Hi everyone, welcome to another episode of Teachly. Today, we're going to be unpacking what exactly an exponent is, the laws behind the exponents, and the definitions of exponents. This will give you a better understanding of what exponents exactly are and the behaviors behind such exponents. It is important that you understand the concept of exponents as they are used in so many different fields within mathematics. So, let's begin. What is an exponent anyway? In simple terms, it is a mathematical operation that shows how many times a number can be multiplied by itself. If we look at the bottom of the page, what do exponents sort of look like? Over here, we've got a variable x to the power of n, where x is our base and n is our exponent. And so exponents are traditionally on the top right of a base. Okay, let's explain this a bit further with a couple of examples. If we look at example 1, we have our standard form, 2 times 2 equals 4, but if we were to put it into the exponential form, we would then have 2 to the power of 2, which is equal to 4. The exponent over here is simply counting the number of times 2 is displayed in the standard form. So for an example, with example 1, there were two 2's, and therefore the exponent is 2. If we look at example 2, our standard form is that 3 times 3 times 3 times 3 is equal to 81. If we were to look at the condensed exponential form, this simply becomes 3 to the power of 4, which is equal to 81. Here again, we are counting the number of 3's that are displayed in the standard form. Since there are 4, we simply put 4 on the top over here by the exponential place. So 3 to the power of 4 is then equal to 81. So now that we've defined what an exponent is, let's have a look at some of the exponential laws, the exponential definitions, and what these all sort of mean. So what is an exponential law? They are mathematical rules that show the behavior of exponents. Okay, well, how many laws are there? At a school level, there's approximately 5 of them. On top of laws, we also have exponential definitions, which sort of add more information to the laws, and they couple the laws quite well. To which we have approximately 11 definitions. Okay, let's go a little bit away from the theory and start using the application. Let's unpack exactly what exponential laws are, what exponential definitions are, and their corresponding examples. So let's start with the exponential laws. Law 1 is as such. If I have a to the power of m times by a to the power of n, the answer to this is a to the power of m plus n. And therefore, if we multiply two common bases together, the exponents add. Let's give an example. If I have 3 to the power of 3 times by 3 to the power of 5, the answer to this will then be 3 to the power of 3 plus 5, which is the same as saying 3 to the power of 8. Over here we have the same bases, different exponents, and because of the multiplication, the exponents simply add. Let's go to law 2. Law 2 states that if I have a to the power of m, and I divide that by a to the power of n, that my answer will be a to the power of m minus n. So law 2 is almost the opposite of law 1, whereby in law 1 we had a multiplication of the two bases, meaning that there was the addition of the two exponents. In law 2, because we've got a division, it means that the exponents will be subtracted from one another. Let's give an example. If I have 2 to the power of 8 divided by 2 to the power of 3, I will then have 2 to the power of 8 minus 3, which then becomes 2 to the power of 5. Okay, let's move on to law 3. Law 3 states that if I have a bracket, a to the power of m, close bracket, and then I have another exponent on the outside of the bracket, n, that the two exponents will multiply together, and the solution will become a to the power of m n. Let's give an example. If I have 3 to the power of 6, bracket, so then to the power of 2, the solution will then become 3 to the power of 6 times by 2, which then equals 3 to the power of 12. Let's go on to law 4. Law 4 states that if I have a variable a, b, close bracket, to the power of m, where m is the exponent outside the brackets, then what happens over here, let me just get a pen, is that this m gets distributed into the a and gets distributed into the b. So my solution will then become a to the power of m, b to the power of m. Let's go through an example. If I have 3 times by 4, close bracket, and I then multiply this by x, my solution will then become 3 to the power of x times by 4 to the power of x. Let's go through one more example of this, because this law is quite important. Let's make this example 2. If I have 2x to the power of 3, y to the power of 2, close brackets, to the power of 3, then my solution will be 2 to the power of 3 times by x, 3 times by 3, y, 2 times by 3. So the solution then becomes 2 to the power of 3, x to the power of 9, and y to the power of 6. Let's go over our last law. Our last law is stated as follows. If I have a bracket, a over b, close bracket, to the power of m, then what happens over here is that this m gets distributed to the top of the fraction and to the bottom of the fraction. Therefore, my solution is as such. A to the power of m over b to the power of m. Here is an example. If I have, open bracket, 3 over y cubed, close bracket, and this is all to the power of 4, then my solution is simply 3 to the power of 1 times by 4 over y 3 times by 4, which means I get 3 to the power of 4 over y to the power of 12. So this concludes the laws of exponents. Now we're going to unpack the exponential definitions and see how these have relation to the exponential laws. So let's go over the first definition. Firstly, if we have a base to the power of 0, then this will always equal 1. So regardless of the base, if the exponent is to the power of 1, rather 0, then the solution is always 1. So let's give an example. If I have 10 to the power of 0, this is equal to 1. If I have 1,000 to the power of 0, this is also equal to 1. If I have 1,000,000 to the power of 0, this is also equal to 1. So any base to the power of 0 will always get you the answer of 1. Let's go over definition 2. I just need to add some more pages. There we go. Okay, perfect. Definition 2. If I have a base which is equal to 1, I can have any exponent and it will still have a solution of 1. Let me give you the actual definition. If I have 1 to the power of a, this is equal to 1. Let's go over some examples. If I have 1 to the power of 1,005, the solution is still 1. If I have 1 to the power of 20, the solution is 1. If I have 1 to the power of 5, the solution is still 1. Are you starting to get the picture? Any base with an exponent of any number where the base is just 1 results in 1. Let's go over definition 3. Definition 3 says that if I have a base with a negative exponent, then the base and the exponent goes to the denominator of a fraction. So let's go over an example. If I have x to the power of negative 6, then my solution will simply be 1 over x to the power of 6. Okay, let's go over definition 4. If I have a coefficient in front of a base that then has a negative exponent, then what happens is that the coefficient goes on the numerator of the fraction, and the base with a negative exponent, in our example x to the power of negative n, then goes to the bottom of the fraction, so x to the power of n. An example, if we have 3x to the power of negative 4, we will then have a solution of 3 over x to the 4. Definition 5. If I have a bracket ax to the power of negative n, then this entire bracket will go to the denominator of a fraction. Since the negative n is associated with both the a and the x. An example, if I have 3x to the power of negative 4, this then becomes 1 over 3x 4. Definition 6. If I have a fraction 1 over a base with a negative exponent, then this goes back to the top. So it becomes x to the power of n. An example, if I have 1 over y to the negative 6, the solution becomes y to the power of 6. Definition 7. If I have a fraction a over x to the negative n, then this denominator goes to the top and becomes ax to the power of n. An example of this would be if I had 3 over x to the negative 6. To simplify this, I simply bring the x to the power of negative 6 to the numerator. So it becomes 3x 6. Almost there. Definition 8. If I have a fraction 1 over a coefficient a with a base negative n, then what happens is that the base remains, in our case a, at the bottom of the fraction, and the x to the power of negative n then goes to the numerator. So an example would be if I had 1 over 3x negative 5. Then my solution would be x to the 5 over 3. 3 more definitions to go. Definition 9. If I have a fraction 1 over a x to the power of negative n. Then all we need to do is bring the bracket to the top. So this becomes a x n. An example would be if I have 1 over 3x to the power of negative 4. Because of the negative exponent, the entire bracket then goes to the top. So this becomes 3x. We bracket this to the 4. Last two definitions. If I have a bracket a over b, and this is all to the power of negative n, then the a and the b flip. So this then just becomes b over a n. You see what happens here as well, is that the exponent becomes positive. The opposite is also true, in that if I have bracket b over a, bracket to the power of n, and I want to have a negative exponent, I can just flip the b and a again. An example of this would be if I had 3 over 4 to the power of negative 2. What happens here is that if I want a positive exponent of 2, the 3 and the 4 rather, just simply flip, which becomes 4 over 3. Last definition. If I have a fraction a to the power of negative m divided by b negative n, then this simply becomes b to the power of n over m, or rather a to the power of m. So because of the negative exponent, let me make that a bit neater, this will go to the bottom. Because of this negative exponent, this will go to the top, and that is why we have this as an answer. Example, if I have x to the negative 5 over y to the negative 6, this then will become the y to the negative 6 will go to the top, so this becomes y to the 6 over the x negative 5 will then go to the bottom, so it'll become x 5. And there is your last definition. So, what did we learn in this lesson? We learned what an exponent is, what they look like, classical examples of exponents, what exponential laws are, how many exponential laws we have, how many definitions we have, all the various laws that come with exponents, and every single type of definition at a school level for exponents. I hope that you learned a lot from this lesson, and I hope that you really enjoyed it. If you did, please remember to like this video and to subscribe to my channel if you would like to see more content like this. I hope that you have a great day further, and thank you.